Okay, well, today is the virtual lab for the in-person labs we had in the field on the 21st and the 22nd of April in the year 2021. So, the purpose of this lab was to focus on estimating abundance of birds using point counts. And there are a few things I want to do just to get you set up to thinking about the type of data that we're collecting and how that's different than what we've done so far in the class. So these images kind of illustrate that. Birding is what we've been doing so far. That's been going out to try intentionally to find as many different species of birds as possible, and using whatever means you can to do that. And sometimes that means drawing birds into you by pitching or using owl calls or something like that. But what I'm talking about today, and the focus for this week's lab, is a much more rigorous and standardized methodology of doing a bird survey. So in this case, typically you've got an observer who is occupying one location, not moving around, and over a set period of time and using set methods, recording all the birds detected either visually or orally. And that's really important. We have data and estimates for actual abundances of different species of birds. And you're seeing that. This is from the Partners in Flight database of bird populations. And for example, fox sparrow. Here's fox sparrow. And 35 million fox sparrows are estimated to exist. American tree sparrow, 26 million. Dark-eyed junco, quite a bit more abundant at 220 million. And then things that are a lot less abundant, like Bell's sparrow, at only 270,000. So we have estimates like this. And when you look at the sources of those data, in some cases they do come from programs like eBird, but you'll see on almost every one of these BBS, BBS, BBS. So that's the North American Breeding Bird Survey. And the Breeding Bird Survey has to have standardized methods to be able to do this. For example, do we really know that fox sparrow is that much more abundant than American tree sparrow? And if we do, how do we know that? So that's what we want to explore in this lab with the methods we're going to be doing. All of these estimates have really wide confidence intervals around them. But so if we even sort of shoot the middle and say we've got 220 million dark-eyed juncos, do we really know that they're that much more abundant than fox sparrows and harrow sparrows? And how confident are we in those data? Well, that confidence and our ability to have that confidence is largely predicated on the quality of the data that's input. So here is an example of the sort of information we get from the North American Breeding Bird Survey. Again, this is the primary method to survey especially songbirds and other land birds like woodpeckers and mourning doves and hummingbirds and things like that. These are species that are very often detectable by sound, meaning that they're singing or otherwise frequently calling on territory during the breeding season, during, say, mid-May to maybe mid-July, depending on latitude. But here's just an example of the type of information you could get from the Breeding Bird Survey, and you might have seen things like this in various formats. But here are some data for grasshopper sparrow. This big map, of course, is just showing what is the primary data source for the information on that species. In this case, this is a species that is recorded in both the US and Canada. But what you're looking at here is trend data. So these are trends in estimates of number of individuals detected per route. From the beginning, from 1966, which was the first year, all the way to 2019, which is the most recent year of data in the Breeding Bird Survey database. So in this case, we've got a species that's obviously declined over time and enigmatic of a lot of the grassland birds and their plight. This is the sort of information we can get from the Breeding Bird Survey. Breeding Bird Survey, of course, takes place along routes or routes, and there are about 4,000 of those. Maybe about 3,000 are active at any given time. They're indicated with little red dots on this map, mostly in the U.S., but also plenty of them in southern Canada. And each one of these red dots indicates a 25-mile long route on the ground. And at along each of those routes, somebody stops every half mile to count all the birds that they can see and hear over a 3-minute sampling period. So that's the BBS. That's how that works. Here's an example blowing up a little bit and zooming in. So there's a start point and traveling along a road or a trail for that entire distance, and then every one of these stops, someone is doing a point count for birds, meaning they're in one location writing down everything they can see or hear during a set period of time, and that period of time is 3 minutes. This is why it's so important to be able to quickly identify birds, especially the common ones, so you can get those data quickly on your data sheet and focus on the other things you might be hearing or seeing. In Oklahoma, of course, we have a bunch of these too. Here's a little blow up of the area where I do my breeding bird survey route, which is Lookout. This is the Kansas border right here. And all of these little black squiggles are where you've got a starting point and then the sort of location of that route, generally roaded. The red ones here are currently available routes. So if you feel confident in your ability to identify birds, especially by sound, and you want to take part in the breeding bird survey, there's nothing stopping you from do that. It's an all volunteer force, and we could certainly use you. Here's some of the data from my route up at Lookout, Oklahoma, which is mostly, it's probably at least 2/3 sort of native grass rangeland. And, so my most recent one, which was 2019, I had 698 individuals of 47 species. So all of these are species I've got to be able to identify by song and call. Or if I just happen to see them flying by, like I wouldn't necessarily recognize the call of a great egret or a turkey vulture. But generally, you need to be good enough to identify the species you're likely to encounter in a particular area. I wouldn't feel comfortable doing a point count, say, in coastal Oregon or something like that, because I'm less familiar with the bird songs there. So it's recognizing both what you're having confidence in what you know how to do, but also recognizing maybe what your limitations are without some additional practice. In general, any kind of bird survey like this, where there are standardized methods, has a number of objectives. One would just be the basic, well, what species are there? It's a survey, a basic inventory of what species might be at a particular location. That's step one. That's 1 and 0, occurrence or non-occurrence. Better, and what we're usually trying to do, is estimate abundance for each species. And it's not just the total number of species that you find, but also the total number you find in the set area. So we often see these data then translated from abundance into density, so the number per unit area. Within a species, so let's say I've been sampling grasshopper sparrow or eastern meadowlark or something like that on the same route for years and years and years. We want to be able to use methods that are standardized, for one, that we can track that species abundance over time. So within a species, we want to be able to compare abundance over time, and that gives us information on population trend. Is it increasing, decreasing, staying the same, all over the map, whatever. We also want to be able to collect data with enough confidence that we can compare abundance and or density estimates among different regions or different states or different habitat types. So do we know that the abundance estimate we get for Kansas is comparable to the abundance estimate for the same species we might get in Oklahoma? Do we know that within a state or within a region that the abundance estimate we get for the species in riparian forest is the same as we might get in shrubland, or at least is directly comparable to that? So we want to be using standardized methodology that lets us do that. And then it gets really complicated when you consider that there are so many different species. So there are, I think, 538 species in North America that are detected by the North American Breeding Bird Survey, and we want to compare abundance of those directly for as many of them as we can. And we want to be able to say, especially for things that are really broad-based, if our data say that there are 100 Carolina chickadees and 20 white-breasted nuthatches, are we confident that the chickadees are really 5 times more abundant than the nuthatches? So it's not just looking at any one species and tracking its population, it's also figuring out which ones are more abundant than others, and that's what we saw in that Partners in Flight database a little while ago. Now, counting birds brings in, a lot of variability. And the key thing to be paying attention to, what we really stress, is methods that help us account for detectability. And we could just define that as the rate at which objects are tallied during a survey. Any kind of survey and any kind of objects. And we'll express that as a proportion. Species, of course, are going to differ widely in their detectability. Especially for a count like we're doing, like a point count where you're standing in one location and you're recording everything you see or hear. Some species are much louder than others, for example. Others are not only louder, but maybe they sing more frequently, so they don't have long pauses between when they're singing. And these are things that make it more likely for you to detect one species over another. So my example here is dickcissel is generally a lot more detectable than ruby-throated hummingbird. Dickcissel is louder, sings more frequently, and it has this behavior in which it's almost always seeking an elevated perch. So even if you can't necessarily hear it, you're likely to see it on its perch. Much more likely to see it than you would, let's say, a hummingbird, especially at a distance. So if you're close enough, you're going to detect that hummingbird too. But detecting a hummingbird at 200 meters is really unlikely. Detecting a dickcissel, super easy. So all of these different things affect detection rates for different species. Some are more visible than others. Some are secretive and quiet compared to others. Some, sing frequently, and some do not. Some only sing a few times. Unlike things that are stationary, like trees, birds are moving all the time. So we're trying to detect sort of their location as well. And then distance is important because every detection is 100% if the thing's close enough to you. But with all these variabilities in different types of detection, distance is going to affect that too, where some remain detectable out to longer distances than others do. Distance is so important that there's an entire type of sampling that we call distance sampling. And in distance sampling, you don't necessarily have to be stationary and estimating things out to various distances. Distance sampling as a separate type of sampling technique can involve like walking a transect and along that line just sort of recording the distance to the items that you're detecting. And we have some examples of that. This example actually isn't even a bird example. It's an example of surveying for the very rare La Plata dolphin along the coast of Brazil and Argentina. And the data are showing you here that in this particular survey, that out to a little bit more than 100 meters, detection was pretty high. So that was 0.8 or higher detection for La Plata dolphin. And in fact, at closer distances, say within about 50 meters, right, detection is really close to 1. So the data are suggesting that if you're within 50 meters of a La Plata dolphin, you're going to know it, you're going to be able to detect it. But that detection has a function that decays over distance. So if you get out to about 200 meters from the transect line, at this point you're only detecting, probably less than 50% of the La Plata dolphins that are actually out there in the water. And detecting those individuals that are out, beyond 400 meters, so now you're getting out beyond a quarter mile, is really low. So maybe you're only getting about 10% of those. So everything that you're going to try to detect has this sort of decay function over distance. And this applies to birds as well as dolphins. But if you know what that is, then you can use that to help you correct for that difference in detection over distance. So if you, let's say, if we're going to say we get 100% detection within 50 meters and we find 14 dolphins within 50 meters, then we divide 14 by 1, and we conclude that the 14 dolphins we found were the 14 dolphins that were there, and there weren't any others. But if we're only predicting that we sample or detect about 50% of the dolphins at 200 meters, and that's different. Let's say in our 200 meter distance band, we observed 3 dolphins. Well, we would then divide 3 by 0.5, which is our detection, and we'll estimate that although we only saw or detected 3 dolphins, there were probably 6 of them. So that's how distance sampling kind of works to correct for abundance estimation at different distances. Now, of course, there are a lot of assumptions that go into this. It's assuming that the density of the dolphins is equal at all distances that are being surveyed. In other words, that if you're traveling along a transect line in your boat, you're not attracting dolphins to you, such that there really are a lot more dolphins within 50 meters than there are 200 meters out, or consequently that you're not driving them away either. And that affects bird sampling too. That's one of the problems with using distance sampling for birds, although it has been pretty frequently used. It's this assumption that you, the observer, have no effect on the location of the things that you're observing. And we already know that to be sort of flawed, a flawed assumption. So that's why I'm not so much a fan of distance sampling. But I can tell you how we've used it in some of our studies here in my lab. So we've done a lot of surveys for grassland birds throughout Oklahoma. And we do about a 400 meter survey radius around a point. But we found that for most of our species, the detection falls off dramatically after about 250 meters. So when I do analysis to actually compare among species, I just truncate the data and only include those individuals that we detected within 250 meters. We still, detect things beyond 250 meters. We just don't use those in the analysis when we're comparing among species. Now, that's fine for doing work like I do, where I'm doing most of the counts myself, or it's some people who are working with me that I've trained, and we're spending a lot of time in the field together. But for a huge program like the Breeding Bird Survey, where you've got different people participating over time and different people participating over space, that's another bit of complexity. So let's say we've got a blue jay that says something that a blue jay might say. Lots of different people are going to vary in their ability to hear or recognize that. And that introduces a whole other type of bias in the data, which is that species don't just differ in their detectability. Species don't just differ in their detectability by distance. Individual observers differ in their detectability of individual species. So it's not just that each species has a detection function associated with it. Each species has a detection associated with it by each observer. And so that gets really complex, as you might imagine, with lots and lots of observers. So we address that, and we don't have to address that in our lab. We're not going to do that post hoc analysis with the data that we collect. All we need to know how to do is to collect our data so that someone can do that with our data afterwards. So someone can come in and do some analysis afterwards and help us figure out actual abundances. So in this example with these lovely stock people, there are 13 different people, 13 different abilities in terms of their hearing or their vision. There may be certain species that they can identify more quickly than others just because they have more experience with them. One of the really important things that the Breeding Bird Survey pays attention to is that so many people will do the surveys for a long number of years. And especially as we get older, and especially for men as we get older, we tend to lose our high frequency hearing first. So a lot of those older birder dudes who are out there and they might be in their 60s or even their early 70s, a lot of times they don't really hear the highest frequency sounds that some birds make in their songs. So is that a bias that's being introduced? Well, it probably is, and that's okay. We just need to know what that bias is. So it doesn't matter so much that people differ in their detection rates for different species. What matters is that we collect the data in a way that we can estimate that and then account for it. And then that's fine. So that's what we're going to do. We're going to use a standardized point count method. But we're going to collect the data in a way that allows us to do another type of analysis called removal modeling. And removal modeling, in terms of what we have to do, is actually pretty simple. It's just keeping track of which individuals of which species we detect in different time bands during our count. We're going to do a 6-minute count in the field, and we're going to record independently those individuals we first detect in the first 2 minutes, in the next 2 minutes, and in the final 2 minutes of the count. If after we amass lots and lots of data about this, we find that there are some species that consistently show up early in people's counts, that means that those species are highly detectable, more detectable than other species. It means they might be frequent singers, for example. And a species that doesn't necessarily show up in any one of these categories, kind of shows up at random in any of the three, that would be one that's less detectable. So figuring that out per species is important. Having enough data to figure that out per species per observer is important too. And again, you don't need to do that post hoc analysis, but we want to collect the data that would allow someone to do that. And that's what we're doing in this week's lab, and that's how we're going to collect the data in our final field time together coming up this week in ornithology. And next I'll show you what that looks like in the field.